very delighted to say that our next keynote speaker, Dr. David Kidwell, is from the Naval Research Laboratory. And I want to thank everyone who's attending here from government laboratories for their persistence, given furloughs, sequestration, and other considerations, for going way out of their way to be here to be part of this very important conference. As many of you know, Dr. Kidwell has made some very interesting measurements, he and his colleagues at the Naval Research Labs. And also, I'd like to stress, too, that Dr. Kidwell I really look up to because he is far more self-critical of his own work than he is of anyone else's. And for all of us, we know how critical he is of our work. So that's a great thing about his approach to science, in my opinion, and objectivity. Dr. Kidwell.
Thank you. I just want to make a comment on the last speaker. I was very impressed by 1 nanovolt out of 7 volts. That's 1 part in... Oh, it's not on? It's 1 part in 7 billion, which I don't even think I could do today with modern technology. I'm sure your thesis was more than a few years ago, just like mine. This talk is really to set off the conference concept of applying the scientific method to understanding LNR, or anomalous heat effects. And its subtitle is Off the Chart. And you'll understand what that means as we go through this talk. Now, if we're trying to understand the scientific method, you got to understand what is the scientific method. And so here's my concept of the simplified steps in the scientific method. First, you make some observation, then you make up some hypothesis, you collect a lot of data to support that hypothesis, you make a few presentations, you write a few papers, and then you win a Nobel Prize and make a lot of money. Now, some people will say, well, first you make the hypothesis and then you make the observation, but in real life what you're doing is you're mucking around in the laboratory, you find something that you didn't expect, and then you come up with an excuse for why it's that way. Now, this is how most people think the scientific method is, but it leaves out one important point. That is the Prime Directive. Now, you haven't, if you just came in, you haven't wandered into a Star Trek convention. That is somewhere down the hill. What the Prime Directive is in science, the Prime Directive is to prove yourself wrong. That is, logically, only something can be falsified. So really, you collect a lot of data to refute your hypothesis. And that's what a lot of people leave out. And the reason you do that is you try really hard to refute your hypothesis. And once you can't do that, then you grudgingly accept that the hypothesis for that given period of time is right. Right? Now, I happen to like this quote: there's no sure way to screw up an experiment than to be certain of its outcome. But we're going to apply the Prime Directive to NRL's data set. Now, I'm picking on NRL's data set because, one, we took it, we know the most about it, and I want to show you how we use the Prime Directive to actually avoid getting egg on our face many, many times in our data set. Now, if the Prime Directive is to prove yourself wrong, every day you wake up and you say, this is the day I'm going to show myself being wrong. I'm going to show that my last 10, 20, 30 years of research is all garbage. How do you live with yourself? Well, some people drink. Other people live for that one moment between proving yourself wrong and making a new discovery, a new theory, a new observation that no one else in the world has made. Right? And being the first to actually disclose it. So you're in that race. Somebody next door is working on it. You want to be the first, but you want to be right. And you want to apply the Prime Directive. So, let's go on. I want to try to give you an idea of what NRL has been doing in this field with a time chart. Okay? Now, I also want to give you an idea of the enthusiasm we have for this and apply the Prime Directive to all our data set. And we do that by calling it the chart of happiness. So this plots not only time, but how you feel during that period of time when you make that discovery or see that new observation in your chart of happiness. Now, first of all, we start off by Fleshman and Pons' announcement in 1989. And I call that off the chart. Everybody and their brother said, how could this be? This is a wonderful discovery. It will revolutionize mankind. That was off the chart. And for me, I wasn't in that field until later on, you'll see. And I'll tell you a little personal story. I heard this. I remember it. Most people remember things like 9/11, 2001, Twin Towers, December 7th, 1941, Pearl Harbor. I remember this. And the reason I remember this is I have a long driveway at home. And it was in the springtime. I was taking out the trash. And I was walking back, and it was a clear, nice spring night. And I looked up at the stars. I said, now we can see those stars. We can visit those stars because of this discovery. So that's how I remember it. So, as other people, NRL jumped into this. And we did a lot of measurements. And found out that this was hard stuff to think about. It was hard stuff to discover. Most of our measurements at that time were negative. All right? But NRL kept into it in a low way. And we'll come back to the chart of happiness later on in 2005 or 2006. We looked at the field, and until something key does, we did not stay in the field very much at all. Okay? So let's think about what is the prima facie evidence. That evidence that's so strong that something unusual really is occurring in this field. Non-conventional is happening. The first prima facie evidence is radiation on demand. If you can turn off radiation, I see it now, I don't see it, I see it now, that is evidence that something non-conventional is happening. We will go into what our data set looks like on radiation on demand. Transmutation, we'll go into this in quite detail. Production of radioactive isotopes, prima facie evidence. Less evidence is isotopic pattern change and production of elements not originally present. We'll go into this in great gory detail. And finally, definitive demonstration of excess energy, and that is a self-sustaining reaction. If it's running over in the corner, producing energy by itself, and it's more energy than chemical, that's certainly evidence that something unusual is happening. First of all, radiation on demand. The short answer is we have not seen a definitive signal. But I want to tell you how we applied the Prime Directive to avoid misinterpreting our data set. Okay? We typically use a sodium iodide scintillation detector, and it has a lot of advantages. It's sensitive over a broad range, it's rugged, non-cooled, and provides some spectral information, although it's not highly resolved. And ours is an 8-inch sodium iodide detector. We have a number of them, and this shows it in a lead cave against our calorimeter here. Now this detector is quite sensitive, and this is a typical background spectrum one sees from radiation in the room. And highlighted in this region is the region for potassium gamma ray at 1410. And if you look at that region, if you put no salt, which is potassium chloride, in the back of that detector, what one finds is the radiation will be constant. You put the no salt there and you see it. So this detector is quite sensitive. You can see very low levels of radiation. Very well. Now, here's one of the ways that we applied it. As others, we were interested in this individual. And we thought we knew what this individual was doing. And we were applying Jan's concept at the time that a gradient, thermal gradient, is required to trigger this effect. So we built a device that looked like this inside of an insulated blanket, where we had a heater around a catalyst bed which was cooled in the center. Okay? And in this thing we had this sodium iodide detector in kind of a lead cave on the side of it. Alright? So we're going to show you the radiation. Here is the typical background that one sees. Nothing remarkable. And we saw that for months at a time. Different metals, different pressures, different heat conditions. What we saw was nothing. Just background. Well, along came this. Background, background, background. Whoops. Big peak. Background, background. Whoops. Big peak. Background, background, background. Another little peak out there. What the heck's going on? My chart of happiness is way up there. Finally, after months of nothing, radiation. What could this possibly be? Let's apply the Prime Directive. Let's look at the data in a little bit more detail. Here's a top-down plot run in your programs, looking at these peaks. And sure enough, gosh, it looks like the radiation there. And if we look at a side thing, there is clear indication. Here's the background, and here's the peaks during those events. Here's the sum of the peak. 2 peaks, radiation, on demand. What could be going wrong? There are clear peaks there. It is not background. What is this? Let's apply the Prime Directive. Well, first of all, you ask, is somebody using radiation nearby? Is there a source next door? Is there a source down the hall? Is there a source below or above you? And the answer is no. But yet we're seeing a peak. But something wasn't right. Something was not right. The system was running for several days before this appeared. Well, that's not unusual. But we didn't do anything. It was just running by itself when the radiation appeared. We've never seen it before. Maybe the conditions we stumbled on were just right. So if we did not apply the Prime Directive, try to falsify this, which is clear radiation, we would have misinterpreted this data. So what did we find? Well, what kind of radiation is it? It could be technetium metastable 99, which has a gamma at 140, which is that peak right there. And it has a half-life of 6 hours. Right? Where in the world does that come? It could be other things too, because there's a long laundry list of gamma rays that come out of energy. Well, as it turns out, an individual had a medical exam, okay, and they were given technetium 99. And they sat next door for about half an hour. They went away. They came back in that afternoon, sat there for another half hour, went away, came back the next day, and we saw the peak. So we had a very sensitive detector. We were certainly seeing radiation. It was certainly in the face that we were running an experiment, but of course they weren't correlated. And so, in this particular case, the evidence for radiation that we see is very weak. And for us, our chart of happiness for radiation on demand is off the chart. Now, let's talk about transmutation, or isotopic anomalies. Remember, in that chart of things, isotopic anomalies, well, the production of radioisotopes is certainly one possibility, and that would be great. Production of isotopic anomalies is the second thing. But you need to be wary of how you're measuring that. And I want to go into 2 concepts, ICPMS, inductively coupled plasma mass spectrometry, and secondary ion mass spectrometry, which most people in this room use to measure isotopic anomalies. The short answer is no definitive result. I'll show you how we apply the Prime Directive to avoid misinterpreting data. Well, let's take an example. Speculation. Palladium plus deuterium goes to silver. Silver is alleged to be created in some heat-producing reactions, and it has 2 isotopes, which you'll go into more detail, silver 107 and silver 109. But, unfortunately, silver is a trace contaminant in palladium, and it segregates when you pass deuterium or hydrogen into the palladium. And we ask ourselves, how does this ratio vary with ICPMS? But first I need to give you an idea of what ICPMS is and how it works. What you do is you make a solution. And then you spray that solution into a plasma, 10,000 degree plasma, which takes those atoms and ions and molecules and breaks them all apart. Okay, so you make atomic species out of any molecular species. Then you extract out of that plasma a few ionized species electrically. You put it into a mass spectrometer. In our case, it's reverse Neer-Johnson, but it doesn't matter. You put it into a mass spectrometer, and you get a mass spectrum. Okay, you put a lot of energy in. You break everything up. Great. How's it work? Okay. So here's a bunch of samples. Don't have to know what they are. Doesn't really matter. But the silver isotopes are roughly 1:1, and what you see is across the board 1:1. And the way I run the ICPMS in this particular case is the precision isn't great, but it isn't bad. And what you note is up there, a couple there, and one down there. Let's look at these in more detail. Apply the Prime Directive to this data set. Let's look at this first. Okay? Now, I appear to make silver 109, We're taking a ratio of 109 to 107. It's greater than 1. That means we're making silver 109 in these two samples. Okay. Is that the case? Well, silver looks like this, and niobium looks like this. How in the world are we getting the niobium oxide in this sample when we put it into this 10,000 degree plasma? It broke it all apart, and then it formed niobium oxide? We forgot one thing. As we're extracting the ions from this 10,000 degree plasma, they get colder. They can recombine. In certain metals, niobium, one of them, likes oxygen. So it recombines from that plasma, forming niobium oxide. If niobium is in that sample, we're going to get a small peak, small from that, but we're down in the trace level because silver is not a lot of it there. Okay? And misinterpret the 109 from silver as being an isobaric, meaning something the same mass, ion. Is there niobium in this sample? Well, sure enough, yes it was, and it was likely niobium interferent. Well, that's okay. I'm happy. My chart of happiness is still very high. Why? We had no idea how it would get there. The nuclear chemistry was cool. We were looking for this ratio. We were looking for the production of 107. We were seeing 109. We couldn't fit it into our theory. We were still very happy. Okay. Well, let's look at this other two. Here's a peak and here's a peak. Here's a case where we're producing silver 107 or mass 107. I was very interested. This was one sample. It was actually a heat-producing sample. Had an abnormal amount of 107. And this is actually run twice. We ran this many, many times. Every time anomalous 107 peak. What could be going wrong? Well, fortunately, we ran this sample here. That also has an anomalous 107. That turns out to be a catalyst support. Never saw deuterium, never saw anything. What's happening in that sample over there may be happening over here. What's happening in this sample, oops, sorry, is zirconium was present. Zirconium forms zirconium oxide, another oxide producing stuff as it's extracted from that. Look what happens. A 107, but not a 109. Then you look at this, and sure enough, zirconium, of all these samples, that heat-producing sample just happened to have zirconium in it. And it was not a silver 107 isotopic anomaly. Okay? Let's talk about SIMS. SIMS is like ICPMS in one aspect. You put a lot of energy into the surface, and you sputter crap off of it. And as the stuff's coming off the surface, some of it is ionized. And then you extract those ions and you go into a mass spectrometer and look at the isotopic ratio. In doing that, a lot of molecular species reform from that ion impact event. SIMS is very, very, very prone to forming molecular species, unlike ICPMS. So let's look at a very famous example, molybdenum 96. The claim was that strontium plus 4 deuterium, we go into molybdenum 96. This is the example that was published. There was excess mass 96. Here's what molybdenum should look like. Strontium was present. You could have a reasonable hypothesis to make mass 96. Is that the explanation for this? Unfortunately, there could be another one. If instead of examining just this region, you look at the bigger picture, it looks like this. Okay? Here's our mass 96. Here are the isotopes of palladium. What the heck is out here? This is palladium plus mass 40. Uh-oh. Molecular species are appearing there. What if we take 40 from 96? What do we get? 56. Iron is present. Iron is kind of monoisotopic. So iron plus 40 will give you mass 96. Just like palladium plus 40 will give you that mass pattern there. And it will look exactly like this as an iron calcium species. So is this evidence of forming mass 96? I don't think so. Now, other people make mistakes. We do too. And this was actually published in the early days of cold fusion. When you wanted to beat the guy next door, you wanted to be first. So this was published here. This was a positive sample that went through deuterium, and this is the palladium isotope region. Here's what palladium should look like. Here's what they observed. And what do you note? The 106-105 ratio is completely abnormal. So is the 108. So is the 110. And you have a 107. Look, silver's being produced. What could explain this? Well, again, it's our zirconium oxide. That pattern fits this data set identically. So, molecular species can confuse isotopic patterns. Be very wary when you're looking at SIMS data. Be very wary even when you're looking at ICP-MS data, because they're not perfect. You need to understand how the process works. And for NRL, our chart of happiness based on transmutation on isotopic patterns is off the chart, guys. You guys got to get into this. Okay. Now, if you can't see isotopic pattern differences, and you can't see radiation, what is left? And that is the appearance of species that were not present initially. And the best documented claim is the transmutation of cesium into praseodymium by MHI. And what they had at the time is they were claiming that they were adding 4 deuteriums, just like they were doing the strontium, from this very unusual species under very unusual conditions. Now, NRL tried to reproduce that early on, and they did not succeed. We collaborated with MHI. We initially saw praseodymium based on accelerator mass spectrometry, and eventually ICP-MS at parts per quadrillion levels. That's 10 to the minus 15. And NRL was convinced it was praseodymium was present in some of these samples. We attempted to build instrumentation. We built this kind of instrumentation, we built that kind of instrumentation. We were not sitting on our hands. We built lots of instrumentation, we ran the instruments, and we saw buckets, nothing. And it could have been because this is a very complex, multi-layered structure, and we hadn't achieved the ability to make this structure. So we collaborated with MHI in a joint research project. And this is where I got involved. Off the chart. Finally, after some 16 years, I can get into this field. I jumped in with both feet. We volunteer at NRL. We have to work to get into programs. We don't get assigned things as some people believe. We actually have to put proposals together. We have to defend the proposals before we get into this project. I wanted to get into this project, so I jumped in with both feet. And what we had was a piece of metal made at MHI, which they had 1/3 extracted at MHI, and the other 2/3 were sent to NRL. And I was tasked to develop the ICP-MS procedure to analyze this little corner here. And it took about 1.5 years to do so, before we even touched this foil, this precious foil that we got in the mail from MHI. In the meantime, MHI had looked at this part of their foil, and they graciously sent some of the extraction to NRL that we analyzed as well to see how our methodology compared to what they were doing commercially. Now, the first thing you need to think about before we get into the details is praseodymium is monoisotopic. Unlike the other things, we don't have an isotopic pattern that says, oh, look, something unusual is happening. So the only thing we can see with praseodymium is it present or is it absent? But conveniently, it has a signature for contamination in the environment. And it looks like this. The rare earths are not really rare, believe it or not. They're in the environment, but they look like this pattern here. Lanthanum, cerium, and praseodymium down here. So big, big, small, and neodymium is big. They're in the environment because people use flints and lighters, and once you strike a flint in the room, you've contaminated the whole room forever with mischmetal, which will give that isotopic signature. It will not go away. You will not clean it up. It will be there forever. Okay, but note that if we were to, and as an example of it, rare earths are on money. Again, that isotopic signature. They're in things like hair. Same isotopic signature. Look like this contamination. Now, MHI took that one extract, they analyzed it in their laboratory, and they sent it to NRL, and we analyzed it as well. What did we find? Praseodymium. No lanthanum, no cerium, no neodymium, praseodymium. Pure praseodymium. Looks very good. Looks very good. Not only that, we were very happy. This is a commercial laboratory, Touray. They found 20 parts per billion. We found 19. They found 9.1. We found 9.2. They found 25. We found 24. Hey, we're doing pretty good. Now this, of course, could have been an accident. Or it could have been we were doing very good. So we agreed. We found praseodymium. Doesn't have the right isotopic signature. Let's take that 2 years now worth of work and look at the other part of the foil. All right, so we got the other 2/3. Let's start looking at it. Look at this part here. We did. We found nothing. Zip. No praseodymium whatsoever in that part of the foil. We then said, well, you know, maybe it fell off in the box in transit. We extracted the box. Maybe it was on the tape, packing tape. We extracted the packing tape. Maybe it was in the bag. We extracted the bag. Maybe it had diffused into the surface of the foil. We developed a procedure where we could look at the impurities in the palladium down into parts per quadrillion level. So here's a spiked sample, 1,000 times lower concentration. 100 times lower concentration than was found in those extracts. Here's the spikes, here's the samples, and you can see that we would have seen it if it were present. What could have happened? Well, it's not there. Maybe we looked at the wrong part of the foil accidentally. Maybe it migrates. Well, we could have found it. Maybe it catalyzes reverse nuclear reaction with time. I think that's a pretty good stretch. Maybe it was lost in transit. Like I said, we extracted everything in their brother. We could never find it. Maybe we weren't etching enough. Well, we looked at the bulk and we couldn't find it. So we traveled to MHI and looked to do some freshly extracts. We participated in making new samples in their laboratory. They did the extraction on their half. We did the extraction on our half. We exchanged solutions. We analyzed them. And we found nothing. Negative samples for everything. However, on a whim, we decided to do environmental surveys, just like we do at NRL. Now, I should explain what I meant by on a whim, because I was ridiculed in the popular press on a whim. To me, it meant instead of spending 2 years deciding how to make a sample, or take a sample, analyze a sample, I only spent 3 weeks. And the reason I could only had to spend 3 weeks is because I had 2 years taking environmental samples at NRL, and so I didn't have to spend 2 years figuring out how to do it. And what did we find? Well, unfortunately, we found praseodymium in their laboratory. Pure praseodymium. Uh-oh, problem. No isotopic signatures in this material. How did it get there? Well, what really put it over the top was we found thulium and one other species, which we'll talk about in just a minute. Now, thulium is the rarest of the rare earths. Very unusual. It's also monoisotopic. And it actually has a mass 169. And by golly, mass 169 was in the positive samples, but not in the negative samples. I spent roughly 3 months trying to figure out what 169 was. I postulated initially that it was praseodymium plus 2 nitrogen atoms, which just happens to be mass 169. PRN2. And now PRN2 is an unknown compound, but I said, well, you know, praseodymium in a sample like this, maybe it just happens to be an unusual chemical species. But you could apply praseodymium nitrate, PRN, nitrite, PRN, and we put that in the instrument, and sure enough, that plasma decomposed it, and all I saw was praseodymium. So I was confused until you figured out that this was thulium. How in the heck did thulium get there? Well, we found it in their laboratory. One other thing we found in this thing is the positive samples had unusual isotopic ratio on barium. They had excess barium 137. Isotopic anomaly in this sample. It really was in the positive samples. Unfortunately, they also handled barium 137, pure isotope, in the laboratory. So all the positive samples had thulium and barium 137. We found them in environmental surveys in their laboratory. We found praseodymium in the laboratory. It made sense to us that praseodymium somehow found their way onto the positive samples in their extracts. We couldn't find it because we didn't have our laboratory contaminated at that time. It's certainly contaminated now, but it wasn't at that time. So, molecular interferences as in transmutation, SIMS, be wary, ICPMS, apply the Prime Directive, and for NRL, the chart of happiness for transmutation is off the chart, yes. In the final things is heat or excess energy. The short answer is this is the most defensible result that we've seen. All right? Let me just briefly talk about how we do electrochemistry. This is the classical Fleischmann-Pons type cell. We use an electrode sandwich configuration designed by Violante, Victoria Violante at ENEA. But we also have an internal recombiner. So this entire device is inside the calorimeter, a very precise calorimeter, which we'll talk about in a minute. So we apply a certain amount of energy in, and we measure that energy out with the calorimeter. Okay? The cells that we have eventually designed are all plastic cells. They look like this, that are inside this type of container, which are inside this calorimeter. Okay? And this is the kind of data that we generate out of this. And this is going to be a little hard to understand, but let's go through it. This is the power in and power out, or the blue and the pink. And they're lying right on top of each other, as you would expect, as you step it up and step it down, step it up and step it down, okay? And we then take the difference, which is this black line, and that's shown here in milliwatts, or watts, all right? And you'll see the difference is essentially zero, except for these spikes. And these spikes have to do with the energy that it takes during that transient to heat up the parts in the calorimeter. And you can take and integrate that heat, and it looks like this on the green. So this is the integral of that energy. And so as you're heating up the calorimeter, you'll have a negative deficit of about 7 kilojoules, because that's the amount of energy it takes to heat up the parts in that calorimeter, the inside of the calorimeter. And you get that heat back out as you cool it back down. So you heat it up, cool it down, and eventually you end up with essentially zero over a period of days. That's a pretty good result. Pretty good calorimetry. Now, what did the Fleischmann-Pons really see? In the vast majority of their experiments look like this. They run their calorimetry for days, and they see nothing. Then all of a sudden they get some deviation from nothing. We see that as well. But we've always been concerned. We haven't explained this data set. We don't know what causes it, but we're concerned. And we're concerned that this constant heat production is just an offset somehow in the calorimeter. We don't have an explanation for it. We don't believe it's an effect, it's an artifact, but we're concerned. All right? So we didn't focus on this. We focused on something else. But this is how the vast majority of data sets look like. This is what you're trying for. Not big events, nothing like this. This small offset comes in. And you need accurate calorimetry to see this, because you're not going to see it otherwise. You're going to be wandering around in the dark and maybe stumble onto something maybe. Now, many experiments we had the following result. Power in equals power out. Nothing. Here's an example. Constant power in, constant power out. The difference is zero. Nothing. And here's some examples of what we did. I won't expect you to read it, but here's a chart. 140 negatives and, 0 positives. So we said to ourselves, are we going to keep running this for the rest of our lives, or are we going to have some change? So we had some change. We said, what could be going wrong here? All we're doing is running cell after cell after cell and getting nothing. What could be going wrong? So we asked ourselves, is there a difference in how palladium is made nowadays versus how it was made back when Fleischmann and Pons first did their experiments? And the answer is yes. If you look at the impurities in them, what you're going to find is the older lots of palladium had lots of rhodium in it and had lots of platinum in it, and the newer lots didn't. They had zirconium in them, and they had, and the rhodium was taken out, and hafnium was the other thing they had. How that could be is because probably the older lots of palladium were recycled catalytic converters, which has palladium, platinum, and rhodium in them. And at the time, the rhodium prices didn't allow one to extract them. Now they did. So they changed how they made them. They also changed how they actually melted it. Now they're using zirconia crucibles. In the old days, they used alumina crucibles. So the impurities are different. So we said, rhodium. Well, this is parts per million. We're going to put more in. We're going to put in 10%. If a little's good, a lot's better. And we picked 10% for a reason, because it's on a phase boundary, but a little's good, a lot's better. And so we ran our samples, and we made some additions, Raney nickel, cobalt nickel, and lo and behold, we saw this. The first one out of the box, we saw this. Everything was in balance. We added nickel sulfate, and we saw this giganto amount of heat being produced, 10 kilojoules, which is a lot of energy. It's like the energy of a rifle bullet. A lot of energy coming out of that imbalanced cell. How could that be? It's not chemical. It's too big for that. We, to this day, do not have an explanation for this. But this is what we were striving for, time and time again, these big events. We rebuilt these cells. We said, is it an instrumental artifact? We redesigned everything that we did. We kept at it, kept applying the Prime Directive at this data set. We found a couple of other examples. Here's cathode 60, 2 big events, which if you took the cumulative energy, 25 extra kilojoules, from time 0 that we didn't put in that cell, we're getting energy out. We could account for every watt going in, and it was greater than that. All right. And here's some blow up of those. 18 kilojoules and 14 kilojoules. Big events. Now, these big events are very rare. If you look at the data sets, Ed Storm saw about 5 out of 90 SRI, 4 out of 26. We'll come into that a little bit. 4 out of 61 if we take a subset. Energetics about 8 out of 800. Very, very rare events, but they're not chemistry. They're too big for that. What could they be? Well, let me tell you an example of how we selected the SRI data sets. We had this data in our hands, and we were very impressed by this straight line. The human mind likes straight lines. They like correlations until you realize where that line comes from. They're actually plotting X versus X. When you plot X versus X, you get a straight line. Sure enough. Okay? But we have that data, and we were able to look at it in slightly different, and it looks like this. On a log plot, and I don't like log plots, I like linear plots, and it looks like this. And so these are the 4 that we attempted. Now, I don't see the correlation here that others do, but I'm not as smart as other people. So I look at this data set, and I don't quite see that correlation, but we picked these 4 as the excess heat events in our data set that we give an example of. Okay. We need to be careful of instrumental artifacts. And we saw roughly 6 of these large events. We can dismiss at least one of them as an instrumental artifact, as an instrumental artifact doing to a short. We can't dismiss them all. And the thing turns out to be, if you short our system in a certain way, the power supply doesn't know it. The power is nearly sufficient, but not always, sufficient to make the observed effect, shows no error messages, gives RF if you do it in a certain way, but not all the time. The cell has to have the right resistance, it has to have the right power supply, it has to be in the right mode, has to be shorted to the right location, at the right resistance. Then you see this effect. Did it happen always? We don't know. But at least in one case, we are convinced that it did. It could have happened in the other one as well. So with that caveat, for NRL, our chart of happiness for heat is at 25%, because we're not absolutely certain of it. Let me give you, in conclusion, real quick, gas loading. I think I have about 5 or 10 minutes. Okay. I want to talk a little bit about gas loading, but I want to give you a warning first. I want to give you some history lessons on Langmuir. Langmuir worked at GE, and his goal was to build a better light bulb. This was back in the early 1900s. They wanted to build a better light bulb. They had a tungsten film that didn't last very long. The concept back then was the better the vacuum, the better the light bulb. They couldn't pull the vacuums at all back then. So he tested various gases, and what he observed was hydrogen gave extra energy on the surface that other gases didn't. They measured the temperature of the outside of the envelope versus the gas inside. They said hydrogen gave more heat on the outside than the filament. What's going on? What they figured out eventually is what was happening was the hydrogen would split into radicals, and the radicals had to have a third body combined on the surface, releasing the energy. Only hydrogen will do this. Helium won't do it. Argon won't do it. Nitrogen won't do it. Only hydrogen will do it. So if you just measure the temperature of that envelope, you get the impression that hydrogen gives you extra energy, when in reality all it's doing is transferring it more efficiently by 2 processes, convection as well as chemical. To give you that picture, here you have a hot filament. Is this catalyst just right for making hydrogen radicals? I want to hope my chart of happiness will be off the chart if calorimetry is done accurately on the system, and that will tell us, rather than just hotter on the outside versus on the inside. Okay. Now, as I explained in ICCF previous meetings, we had a concept that if we grow particles in situ, we can get some extra energy. And we built an engine running on this extra energy, and it's a Stirling engine, and it looks like this inside of this constant temperature incubator with a bunch of instrumentation. And the actual thing has 2 graphs, RPM and NTCs here. And I want you to follow this graph versus time. How do we do it? Okay. All right. If we get it working. It doesn't look like we're going to get it working. I guess I have to do clicking. Yeah. So what you'll see is the engine's off, if I pick the right one, and it starts up, okay? And it starts up and runs because I put electrical power into it, and then at a certain point in time, I actually apply hydrogen to it, which I picked the wrong movie, sorry. And what you should have seen is the hydrogen, when it's introduced into this catalyst, gives you enough extra energy to increase the RPM on that engine for quite some time. At the time, we had to apply electrical power. I can report today that we can have this thing run entirely out of the heat from whatever the source is, chemical or something else. So you can get an engine running on whatever this source is. Do we know it's not chemical? No. We're still applying the Prime Directive. Every day I wake up and say, you know, today is the day that I'm going to make the last 2 or 3 years of my life worthless because we haven't checked the last box to get rid of the chemical energy. So the control that we're worried about is hydrogen deuterium approximation. So for NRL, our chart of happiness for gas loading is at 50%. We're not sure about that. So what do we observe? We really observe no evidence for nuclear products. We observe no evidence for transmutation. And the evidence for excess heat in electrical chemical cells is we can't rule out all instrumental artifacts. Evidence for gas loading is all possible chemistry is not ruled out. So after 20 years, not much. But we still believe the phenomena deserves further study. Now, in closing, I want to give you a plea. And the way I do this is by describing the 3 greatest gifts you can give a curious individual. The first greatest gift you can ever give an individual is possible. And what I mean by that is someone somewhere in the world has accomplished this feat. It's possible. Somebody did it, at least once. That's the best gift you could ever give a curious individual. I can do this. It's possible. Not just theoretical, not somebody came up with a theory. Somebody actually reduced it to practice in patentees, right? It's possible. The second thing, it's practical. You can do a lot of stuff in the world, but this is something that's possible, and I care about it. I want to solve the world's energy crisis. I care about this. Okay? So it's practical and possible. The third greatest gift is a mixed blessing. It's secret. And the reason that's a mixed blessing is for 2 reasons. Let me see if I can explain. By keeping it a secret, I keep that curious individual working as hard as they possibly can. That person over there in the corner's done it. I want to do it too. But they're not telling me. But also keeping it secret is a detriment to them. Why? Because they don't control it anymore. They keep it secret. They show it's doable. I'm working as hard as I can. They don't control my thought process. Maybe I will come up with a better way to do it. They probably didn't think of the right way. They show it's possible, but they didn't think of the key ingredient. I may come up with a better way and take over. And I want to close in the following things. Wright brothers airplane. Just as Rob Duncan had said. They launched in December 17, 1903. They were not the first to fly. Many people flew before them. They were not even the most well-funded. Langmuir, who was a very famous scientist at the time, had $50,000 from the federal government to make heavier-than-air flight. It was a fortune back then. He didn't get off the ground. The Wright brothers, what they did is had controlled flight. They were the first to do controlled flight. That was the great convention. And they kept it a secret. They did the first demonstrations, but they kept it a secret as their patent was being granted. Now, Curtis, in 1907, was in collaboration with Edison. And Edison said, we don't want this to belong to one individual. We want a group effort. Let's form a consortium and get this to work. Share knowledge. Curtis came up with an idea and formed the Curtiss-Wright Company in 1910. Okay? Curtiss actually invented the flaps on the wings. So when you fly today or tomorrow or whenever, look out of the air wing, that was Curtiss's invention. Curtiss actually had a better idea than the Wright brothers, showing it was possible. Curtiss made all the airplanes in World War I. 50, I think, a week. Or was it 500 a week? Some large number a week. Wright brothers made none. 0. They had a patent, and the concept at the time is if it flew, they sue. Okay? And they spent all their resources fighting people that were copying what they thought were their ideas. But Curtiss formed in 1929 the Curtiss-Wright Corporation. Notice the names. Curtiss-Wright Corporation. Not the Wright Curtiss Corporation. Now, the Wright brothers didn't die, of course, unknown. They got their name on coins. Right? Not Curtiss, but the Wright brothers. So, I want the rest of your stay here to have your chart of happiness be off the chart. Hopefully you will be impressed by other people here. Hopefully you'll look at their data sets. Hopefully you'll apply the Prime Directive, and you will come away, one way or the other, off the chart. Any questions?
I'm Yasuhiro Yuamura, Mitsubishi Heavy Industries. He mentioned about transmutation experiments. I am the Mitsubishi Heavy Industries member. And I would like to comment about his presentation. I would like to say that praseodymium detected by experiments cannot be explained by the contamination he mentioned. David Kidwell measured praseodymium in the balance of our laboratory. He detected. But we performed 9 samples, and the 3 samples are foreground sample, permeated sample. From only 3 samples we detected. We, Mitsubishi Heavy Industry and Naval Research Laboratory, detected 3 samples for praseodymium. But we could not detect praseodymium from other 6 samples. If these samples are praseodymium contaminated by the balance for measuring mass of the palladium sample, 9 of the samples should be contaminated by praseodymium, but only 3 samples. So it is very difficult to explain by the contamination story. And the other one point is transmutation of cesium into praseodymium is reproduced by other researchers. For example, researchers of Toyota company, Toyota Laboratory, they presented their results, reproduction from cesium to praseodymium at ICCF 17. That's my point, that's my comments.
Can I just comment for one? I perfectly agree with you. Only thing I can speak for is our data set. I cannot speak for replications after we stopped working on this subject. There are other replications of the MHI work that have made claims of transmuting cesium into praseodymium. I have not been able to look in detail at that data set. But what is published, as it stands, looks very, very good. I'm just concerned that have they really looked at all contamination events?
You want to comment about the contamination, danger of contamination you want to stress?
I'm always concerned that when one's looking at monoisotopic species, that contamination has truly been ruled out.
Okay.
Yes, your point's well made, and I'd also say that we're kind of crawling behind on schedule, but if you'd like to make a counterpoint to the talk you've heard, that's what I'd like to do.
Yes, there's a counterpoint. So, first one, we may be experiencing in the Martin Fleischmann Memorial Project something similar to the palladium difference between old stock and new stock. We've only been using material supplied by Celani, very kindly supplied by Celani, that is of new stock. We have only one 700 layer wire, which is from 1970s process stock, which we are reserving until we've got well down the line in terms of our calorimetry and our measurement. That's one point. The other point about the Langmuir effect, even before we had something that was, we could arguably say there's something interesting going on in December, we thought there was a problem with the type of surface calorimetry and with all the questions surrounding it. So we designed a cell which has basically a Celani cell in a steel shell, and that kind of addresses the Langmuir effect, and I'd like to talk about that later on tonight in our 15-minute slot.
Yes, thank you.
Yeah.
There will be plenty of time to counter.
I was just going to bring up one last. That is actually why I brought that slide up, because I knew the Hunt Utilities Group was working on this. I follow your work relatively closely, and I'm hoping to hear from your calorimetry data so that my chart of happiness will be optimal.